In the previous lecture, we introduced the notion of normed linear spaces, and also we consider a factor space, and we proved that it is possible to make, in fact, out of a factor set, to make a factor space, a linear space. It is a linear space. And we also proved that we can define a norm on this space. And also I mentioned that it is possible to prove that a factor space is a Banach space, which means a complete space, given that the original space is Banach. So today we will prove this, well, in the first part of the lecture. And to do this, we will need some extra preparation. So we will speak shortly about a series in normed linear spaces. Most of the definitions here, well, we will not have many, but the series in non-linear spaces are quite similar in, well, at least in terms of definitions, to the usual series we studied before in calculus. So if we take a sequence, we can consider a formal expression is called a series in E. Well, why do I call it formal expression? Because a priori we don't know whether it's convergent or not. Well, let's now define a convergent series, and the definition again similar to the definition from calculus. A series in E is still the same, the normed linear space. I will not copy it for the second time. A series in E is said to be convergent if a sequence, well, as before, we just consider a sequence of partial sums, Sn, this sequence. If this sequence converges in E, in this case, so if it is convergent, in this case, we write the sum of the series equals to S, where S is the limit of the sequence Sn. Let me state fairly simple criterion for a convergence of a sequence proposition. So if a series converges, then the sequence of its partial sums is Cauchy. So again, you shouldn't be surprised about it. If our non-linear space is Banach space, then the converse is true. Now let's introduce the notion of absolutely convergent series. So we have a series in some non-linear space E. It's called absolutely convergent. If a numerical series converges, well, in R. Every absolutely convergent series converges. So let us take an absolutely convergent series. This means that this numerical series converges by definition, which implies that, or rather equivalent to the fact that the partial sums of this series, of this numerical series, is Cauchy. Which means for every epsilon greater than 0 there exists n, such that for every n greater than m greater than capital N, we have this expression is less than epsilon. But by triangle inequality, we have that the norm of this sum, this expression, is less than this. And we know that this is less than epsilon if we choose epsilon and m like this, which means that the partial sum, sequence of partial sums of the original series is Cauchy. But we have assumed that our space E is Banach, so every Cauchy sequence converges, which means the convergence of series. Which means by definition that the series converges. Okay, now let's go back to our factor spaces. So let me briefly recall the definition of the norm and give a fairly simple alternative form of that norm. So from the previous lecture, we know that if E0 is a closed subspace, of a normed linear space, then the factor space is a normed linear space with the norm. We defined it as follows. So we take an equivalence class and the norm equals to infimum of the difference over all y from E0. Sometimes it is more convenient, instead of writing a equivalence class with its representative inside, like it's done here, an equivalence class with representative inside, just denote the elements of this space by, say, letter, any letter. And then equivalent form, equivalent expression for this norm for any, say, S from the factor space. So I take S to be an element of this factor space. So S itself is an equivalent class, equivalence class. And I will define the norm of S in a factor space as infimum of norms where the infimum is taken over all elements of S. And now let's prove the main theorem of the first part of the lecture. If E0 is a closed subspace and E is Banach, space E, then the factor space is Banach. Let Sn from the factor space be a Cauchy sequence. So we know that starting with some number, well, for every epsilon, starting with some number of n, the elements of this sequence getting epsilon close to each other. So we always can find a subsequence subsequence of this sequence such that minus Snk, so the difference of consecutive elements of this sequence is less than 2 to the power of minus k. Since it's Cauchy, so the elements getting closer and closer to each other, and we always can find such subsequence. So let me also, so here we start over here, k starts from 1. I will add a 0 element to this sequence, and the 0 element will be E0, which is in the factor space is a 0 element. So what do we have then? We have then the sum of all of these terms, is less than or equal, or just less, what can we say about this series? It converges. So this is less than infinity. Now, since the norm in the factor space is defined as an infimum of all elements from the equivalence class, we can always find an element xk from the difference of these two such that the norm of xk is less than or equal to in E, then two norms of this difference that is for every k 0, 1 and so on. But having this estimate and having the previous estimate on this series, we can conclude that this series converges. Which means in particular that the series of elements from E converges absolutely. absolute. We use here the fact that E is Banach, by the previous result in Banach space, every absolutely convergent series converges. Moreover, it converges to some element from E. Or in other words, as we write it, the series equals to X. And now let us set S to be an equivalence class generated by this X. Let us now consider the partial sums of this series. For every integer n, we have the sum from 0 to capital N equals to not equals to, it belongs to, and I will go up to n minus 1. So sum from 0 to n minus 1 of xk. We know that every xk belongs to the difference of these two sets. In every element of this sum, we have a difference of consecutive terms. So when we consider all these sums, pretty much all of the elements cancel each other out. We will only left with the very first one and the very last one. But Sn0, by our construction, the zeroth element, is the subspace E0. And as we proved before, as we considered before, as we discussed before, E0, the subspace E0, is a zero element in a vector space. So addition or subtraction of E0 doesn't change anything. So we have proved that the partial sum of this series belongs to this set. Now let us consider the norm of the difference S minus Sn capital N. By the definition of the norm, it is, or rather less than or equal to. The norm is infimum, so it is less than or equal to. But this difference is a sum from capital N to infinity of xk, which is a tail of convergent series, which this means that it tends to 0 when capital N tends to infinity. Which tells us that a subsequence S and capital N converges to S. But Sn capital N is a subsequence of our original Cauchy sequence. So we have a Cauchy sequence such that one of the subsequences converge, which means that the sequence itself converges. To S and we know that S belongs to the factor space, and we are done. Therefore, the factor space is Banach. So what we do here is we take a linear space and define some norm on this linear space. And of course, there are many ways to define norm on a single space. If you recall the examples on, for instance, Rn, we can define infinitely many norms. So the P norms, there are infinitely many of them. Pretty much the same story on the space of continuous functions on the interval AB. We can define infinitely many norms on this linear space. A linear space with two different norms can be quite different from each other. So for instance, a sequence can be convergent in one norm and cannot be convergent in the other norm. So the notion of completeness in particular is norm dependent. So it's kind of nice to know which norms are compatible to each other in very vague, in a very general sense. Let us introduce the notion of equivalent norms. If we have a linear space, and if we have two norms on this linear space, for the first norm I will use the usual notation, and for the second norm I will use the same notation but with 3 bars instead of 2. So these are the two norms. So we will call the two norms on a single linear space equivalent if there exist two constants both greater than 0 such that this double inequality holds for any element x from a linear space. Well, in particular, a simple example, if you take a single norm and multiply it by a scalar, then you will get an equivalent norm. In particular, it's easy to see from this double inequality that if a sequence converges in one norm, then it is also convergent in the equivalent norm. And well, I call it equivalent, and well, I will write in this case that this norm equivalent to this norm. And it is in fact an equivalence relation on a set of all norms. So let's go for the remark. Let n be the set of all functions from our linear space E into real numbers such that f is a norm. Which means that it satisfies that 3 properties. This definition of equivalent norm in fact defines a relation, an equivalence on this set N. First of all, the reflexivity. Each norm is equivalent to each other, well, with constants, both constants being 1. If one norm is equivalent to another, then the second norm is equivalent to the first norm, that's symmetricity. and the transitivity is also easy to see. So it is in fact a true equivalence relation on the set of all norms. Now let us prove a fairly important result, which tells us that if we are in finite dimensional space, then all norms are equivalent. Let's prove this. Let E be a linear space and let dimension of E equals to n less than infinity. Since the dimension of this space is n, then we can find a basis which consists of exactly n elements. Further, any element can be written as a linear combination of basis vectors. So for any element x from E, we have x equals to xi ei for I from 1 to n. For some scalars, x1, xn. And now let's use these coordinates of x, so the numbers xi, to define a new norm for every, or rather, define a new norm. I will subscript 2 and you will see why. So this is exactly the P norm with P equal to. Let me denote the old norm by a norm with 3 bars. Okay, now let's try to compare the old norm, the one with 3 bars, and the new 2 norm. Let us take the original norm of x. We know that x can be written as a linear combination of the basis vector. So let's just substitute it. Now I will use the triangle inequality to write this as absolute value of xi times the norm of ei, like this. So we have a sum, and every element of the sum is a product of 2 elements. In this situation, we several times use the Cauchy-Schwarz inequality. Let's use it again. This first term here is nothing but our new norm. What can we say about this second term? We can say that it does not depend on x. So it is a constant. It is a constant. And this is what we wanted. So we estimated the old norm by constant times the new norm. M to be this expression we obtain the inequality between the old norm and the new one. And this holds for every x from E. Now we need to prove the converse inequality, the estimate from below. And the idea is going pretty much backwards. So what we did in the first part is we've taken an element, consider the coordinates of this element, and with the help of these coordinates we define a new norm. What we will do in the second part, we will take a bunch of n numbers, and with the help of these coordinates we will define the old norm. So let us consider a function f from Rn sub 2, so the norm will be 2, which is exactly like our new norm, into R, given by. So we will take f of x1, xn, and dimensional, the usual array. And out of these elements, we construct a linear combination xi, ei, and take the old norm of it. Well, I use here Rn and R, saying that our linear space is over the field of real numbers. Well, we consider only two cases when the scalars are either real or complex. So here I consider the real case. The complex case is exactly the same. Just take the functions from bundles of complex numbers into complex numbers, and the rest of the proof will be the same. First of all, what I want to do is to show that the function f is continuous. So I take the absolute value of a difference of the function f at two different, bundles of points, two different arguments. By definition, each of these equals to the old norm of some expression. So I just plug the value of the function. And now we will use the converse triangle inequality. The right-hand side can be estimated by in the first part, we have proved that the norm of this expression is less than or equal to big M times, in this case it will be x minus 1, norm 2. And it's not accidental that I initially considered Rn with 2 norm. So that's exactly what we need for to claim that f is continuous. So the function f is defined on the whole Rn. Let's now restrict our attention and the function f to the sphere in Rn. What can we say about this sphere? There is no doubt that this sphere is bounded. So it's a sphere of radius 1, just take the ball of radius 2, it sits inside. By definition, it is bounded. Also, it's not difficult to show that it is closed. So S is bounded and closed. In general, being bounded and closed doesn't mean much in general metric spaces. But we are in Rn. And in Rn, if a set is bounded and closed, then it is compact. So if now we restrict our function f to the sphere, which is compact, the function is continuous, defined on compact, so it attains its minimum. Well, maximum as well, but we are interested in minimum, since we want the estimate from below. Well, which means that is, there exists x01, x0n from the sphere such that f of x1, xn is greater than or equal to f of x01, x, 0, and, well, nothing is surprising. And I will call this value of minimum a little m. And that will be the little m which we want for the proof of equivalence. But if you remember from the definition of equivalence, this little m should be greater than or equal to 0. So let us show that this is positive. So since this vector belongs to S, so remember that S is a sphere of radius 1. Then we can definitely say that at least one of these coordinates of these x ends is not 0. Thus, the value of f at this point equals to, by definition, the old norm. So, since this vector is not 0, then this expression, this linear combination, is not 0 as well. Because the vectors EI are the basis vectors, so they are linearly independent. So, this element is not 0, and hence the norm of this element is not 0 as well. They are not equal to 0. Hence, little m is positive. Almost done. So what have we proved already? We proved that the value of a function f on any point on a sphere is greater than or equal to m. But let us recall what is function f. So what we have, that for every x in R and 2 such that its 2 norm equals to 1, which means that it is on the sphere, we proved that the old norm of x, which is the value of the function, greater than or equal to m. That's what we have over here. But this is on a sphere. We wanted to prove for any vector x from Rn2. What can we say about the norm of this element? So we know the result for the case when the norm of a vector is 1. Now take an arbitrary vector, well, non-zero. Non-zero. If we take a vector and divide it by its norm, then we get a vector of the norm 1. So it does satisfy this vector inside, does satisfy this condition. So by this, we have that the old norm of this vector is greater than or equal to m. But what we have here in the denominator is just a constant, so we can factor it out. Let me state two simple but important corollaries of this result. So if we are in finite dimensional space and we take any subspace, then it is closed. And this is in fact a very interesting result. Subspace is a subset which is closed with respect to algebraic operations. So if we take a vector from this subset and scale it, will still, the result will be an element of this subset. If we add two elements from a subset, the result still will be in this subset. So when we call about subspace, it is closed with respect to algebraic operations. And we claim that in finite dimension, it is closed with respect to the norm. So the wonderful thing about this result, because it relates the algebraic property and the analytic property. And the second result, any finite dimensional linear space is Banach. Well, to speak about the completeness, we need a norm, any finite dimensional norm. Normed linear space is Banach.